you see it's a, some number of percent in R, and there's the upper limit. And then you run the clock forward and you say in something like 10 years, if you had either CMBS-4 or a space-based mission, or if you combine them, what could you do? You see you're pushing down by at least 1 order of magnitude, if not 2 orders of magnitude. And that's something that could be there in the next, if you really got on your horse and went for it, you could get that done in 10 years. And so this is the space. You see that, and this is the scalar spectral index. You can see that we're just measuring the fluctuations better, but we're also pushing down. And so you could think of this as, this is your gravitational wave detector. We're measuring strain on the scale of the cosmological horizon. So that's where it's at.
Would be compatible with anything you find.
Not anything. I think it'd be really hard to get something, say, out here. So there's lots of stuff that inflation can't do. So inflation is very flexible. I know that you have strong opinions on this, but it's not infinitely flexible, right? So while it's true that it's very hard to rule out the idea of inflation in this plane, it's not wide open. You can't do anything. All right. So that's using the very large angle B mode. So one of the things that's also really, really interesting to look at is the structure of the acoustic peaks, in particular the TE correlation, is sensitive to the radiation density. And, in particular the integral of the radiation density, because that slightly shifts the acoustic peaks. And so that gets parameterized through this thing as delta N effective. For historical reasons, it's parameterized as if it's like a new family of neutrinos, how did that show up? And so imagine that you had some other particle in the universe. And so I think that maybe for astronomers, we don't really think, it's like, well, that's a pretty weird thing to imagine. But just first of all, let's imagine that's true. Imagine there's some new particle. Well, so a new particle, if it was ever in thermal equilibrium with the standard model, which is to say, if it has any if it matters at all to us, right? That's what it means. So if there's any particle that matters, if it was ever coupled to the standard model, it surely was in thermal equilibrium if you run the clock back far enough. And so if it's in thermal equilibrium, you generate some background density of these things, and there's it's just AT to the fourth is the energy density. And then what happens is the clock goes forward. Well, weird things happen in the universe. Like for instance, here's the QCD phase transition. So when the QCD phase transition happens, there were a bunch of particles around. They dump all their energy into whatever they were coupled with, and then they freeze out. So if it was in equilibrium during the QCD phase transition, when that phase transition happens, there's a huge dump of entropy into this sector, which would substantially increase the energy density in that. So this is how much energy density is in this light particle, and so that's going to depend on the spin, because that's the number of degrees of freedom and things like that. So the QCD phase transition happens. So if it was in equilibrium when the QCD phase transition happened, if it didn't freeze out till somewhere in here, it picked up all that extra entropy, and you'd see that it would have some actually detectable level of contribution to the radiation density today, such that it's actually already ruled out by Planck. So something that decoupled fairly recently, say just before BDN, actually would contribute too much excess radiation density in the universe. So then you say, okay, well, let's measure what the radiation density is and go backwards. And what you see is that as the experiments become more sensitive, so as you go down in that CMB survey plot in terms of sensitivity, what you see is that you're pushing down and you're improving your measurement of the radiation density, and you're going back in time. And so you can, with CMBS-4, for instance, you could actually rule out any particle freezing out after the QCD phase transition. That if it was around and was in equilibrium during the QCD phase transition, it would have picked up too much entropy to be consistent with observations. And yeah, that's an interesting particle physics experiment. But where it really comes out is, oh wow, that's so Dan Green wrote a really nice white paper on this. So while you think that it's really weird to have excess particles around, lots of people will say, oh, well, maybe dark matter has some weird extra interaction. Well, you know what, like, if dark matter has in any form of interaction, usually that gets mediated by some particle, and most interactions get mediated by, it's usually a light particle of some kind. So for instance, people that want dark matter to be interacting with baryons, let's say you want to explain edges or some other thing you want to do. Let's say there's some cross-section of interactions between dark matter and baryons. Well, that has to get mediated by some force in most models. And so usually that force is a light particle. Interacting with a baryon means that it was in equilibrium with the standard model. And so what you can do is you can then just put limits on the dark matter baryon cross-section as a function of whatever your mediator mass is, purely based on the fact that you would have produced a bunch of these in the early universe. So if you see someone has a model for some interaction between either self-interaction with dark matter or dark matter standard model interactions, invariably, one of the first things that gets put in is a constraint on, well, whatever this interaction is, we can't produce too many light degrees of freedom such that we blow this constraint on the radiation density. So this is actually a quite restrictive particle physics experiment, just looking for new interactions. So, and it's not just particle physics, we also care about how dark matter interacts with itself. So there are astrophysical repercussions to this particle physics. All right. So that's the particle physics part of it. Now, let's just shift into some of the more astro things. So this is the North Pole. So I'm sure you all see Polaris at the center of this field. No, you don't, because stars aren't bright in a millimeter. So Polaris is in the middle of this field. This is the North Pole. And then I'm just going to do a little exercise where so imagine that this light propagated through a universe that was lumpier than the one we live in. And I think it's going to be roughly 20 times larger effect than you would expect. And I put a lump of mass. And so it's going to get lensed. So I'm going to take this Gaussian random field, highly Gaussian empirically, send it through the universe, we're going to lens it. And then let's see if you can see, if it was a big enough effect, how you'd be able to tell what happened. So something happened, right? But it didn't change the mean, right? So you'd say, okay, well, statistically, what happened? So it's not brighter there, right? The mean intensity is 0 everywhere on average, right? It's a Gaussian random field. Didn't change the intensity. What it changed was the spatial correlation pattern, right? So here you see the spots are bigger than they are here. And then you see there's some anisotropy here, that's shear. And so what that's saying is that the 2-point correlation function is no longer isotropic, that's been stretched in this direction, or in this direction, or in this direction, in a way that's correlated with where the mass is. So your eye is actually doing an estimator of the 2-point statistics in the field. You may not have realized your eye did that. Maybe your brain's doing it, but anyway. So what does this mean? Well, it means that you could actually just go looking for weirdness in the statistics of your map. And so in particular, so this shear estimator, so this shear that happens is really the bad one for turning E modes into B modes. So you have that polarization direction. It's varying this way. Well, shear does this weird thing where it's gonna take things and it's gonna shift them. So this spatial pattern that was changing this way is now gonna be changing at some different angle. And so it's turning some amount of the E modes into B modes is the shear. But you can run some statistical estimator that says, well, let's just look for how the statistics vary as a function of position across here and use that to figure out where all the lensing took place. So that's what people do. So it's a 2-point estimator. So the easiest thing to do, is use the 2-point estimator, and that's a quadratic estimator, 2 points. And so you can do that, and you can make maps. So here's a map of the gravitational, so I think this is the deflection. So with the SPT map, so this is something that Kimmy Wu is working on at the University of Chicago. So this should be coming out imminently, probably in the next week or so. So this is a map of the gravitational potential from those SPT poles. So those SPT pole maps I showed you, here's the lensing map that goes along with that. This is just a map of all the mass fluctuations integrated along the line of sight. So we reconstructed mass. So we can do power spectrum of that, or you can cross-correlate it with large-scale structure. There's lots of things you can do with that. So So that's one of the things you can do. And so this is, this is exactly what LSST is doing. LSST making mass maps over huge chunks of the sky. And in fact, if you compare the signal to noise per mode of this map with the signal noise per mode of the best current optical shear maps, they're comparable. And on degree scales, this is one of the best lensing maps around when you compare cosmic shear with CMB lensing, and that'll continue to be true for the foreseeable future. That as CMB experiments get better and optical experiments get better, it'll always be true that the CMB maps will be comparable in their signal noise to the shear maps.
Away, so in lensing, the kernel is usually halfway in diameter. So for redshift 1000, what is halfway? Redshift 3?
Yeah, it's about redshift 3.
So we're looking at the mass discipline around redshift 3.
Yeah, but it's a very broad kernel. So there's
So
a lot of
then,
support at
you
low
cross-correlate.
redshift, because it's also true that structure grows as you go to low redshift. And so the fluctuations will be larger on the near side of the kernel than the far side.
But when you do cross-correlation with galaxy service, you really need high redshift service.
Yeah.
And you don't.
Well, so for instance, previous versions of this, we cross-correlate with DES, and you see a huge signal.
Oh, really?
Yeah. And it's just because the kernel's, while it peaks halfway, it still has a lot of support even at a redshift of a half. It's still like a third or something at a redshift of a half. And so, but something you can do with this is you can then take these low redshift surveys and use those and subtract those out, and then you have a map of just the high redshift universe, which you can then use to search for quasars or ionization or whatever you want to do. So there's lots of stuff you can do with this, and it works really well in